In this video, I'm going to share all my secrets for modeling this bike sprocket parametrically and creating the different toolpaths to machine it. I hope to show you through this masterclass that FreeCAD can be used to achieve professional results. As always, you can download the sketches and the 3D files for free to follow along with this tutorial on my Ko-fi page. If you want to support the channel, you can leave a donation. It helps me a lot. Thank you in advance. For this project, we'll be using FreeCAD 1.1. If you don't have it yet, you'll find the download link in the description. Since this project is about CNC machining, it's very important to set the right unit system. Make sure to select metric small parts and CNC, otherwise you might run into problems when entering the correct tool speeds. You can also change the unit system directly in the project, at the bottom right of the screen. To create this part, we'll work only in the part Design Workbench. Once the model is done, we'll switch to the CAM Workbench to generate the toolpaths. If you are only interested in creating the toolpaths in the CAM Workbench, you can just download the 3D model and skip straight to this part. For those interested in 3D modeling, I'm going to model the part as if I were working for a company that needs different sizes of bike sprockets. That means I'll use variables. I've simplified it to just one variable, the most important one, the number of teeth. In FreeCAD, to create a variable, click on the varset icon in the toolbar. In the window that opens, you'll be asked to enter a name for your variable. We'll type number of teeth with a capital letter at the start of each word and no spaces. The capital letter will create spaces between the words in the panel on the left. Next, for the variable type, choose integer, since the number of teeth is a whole number. Then enter the value 44, which is one of the most common sizes for this type of sprocket. Finally, confirm by clicking OK. In the tree view on the left, press F2 to rename the varset to dimensions, so it's easier to identify. Next, we'll create a second variable, which will be calculated based on the number of teeth. This variable represents the diameter of the bike sprocket where the chain makes contact. We determine this value using the pitch circle diameter formula, which lets us calculate the sprocket diameter based on the number of teeth and the chain size. In our case, we're using a standard bike chain with a pitch of 12.7 mm between each link. This formula might look a bit intimidating, but don't worry. Just remember that it lets us get the chainring diameter. Then do as I do. In the table, change the variable type to length, since the value will be a decimal, and give it the name diameter chainring chain. Next, in the left menu, click on the value, then on the FX icon and enter the following formula. 12.7 divided by the sine of 180 divided by the number of teeth variable. To select number of teeth, you can start by typing dimensions to call up the variable. Then click OK or press Enter to confirm the creation. In the Properties panel on the left, you should see the diameter variable appear in blue, which means it's a calculated value. Now we can finally start modeling. We'll begin by creating a flat cylinder that represents the thickness of the teeth. To do this, create a sketch on the XY plane. Then, using the Circle tool, draw a circle starting from the origin. With the Dimension tool, we'll assign a value driven by our variable, so the circle changes size automatically with the number of teeth. Click on the FX icon, then enter the formula diameter chainring chain plus 6.6 mm. This will give us the outer diameter of the bike sprocket. Don't forget to add mm at the end of the formula or it won't work. Next, we can exit the sketch. Then click on the pad tool in the toolbar to create an extrusion of the circle. In the task menu, set the pad operation to be symmetric with a thickness of 2 mm. Then click OK to confirm. Before we continue, let me switch the view to orthographic instead of perspective. I find it easier to understand the shapes this way. Now we'll create a second cylinder inside the first one, which will define the surface of the teeth. Start by creating a sketch on the XY plane. Then, using the Circle tool, draw a circle at the origin. With the Dimension tool, we'll also assign a value driven by a variable. Click on FX and enter diameter chainring chain minus 12 mm. Press Enter, then exit the sketch. Using the Pad tool, we'll create the extrusion. In the task menu, set the mode to symmetric and enter 4 mm, which corresponds to the total thickness of the bike sprocket. Now we can move on to the most interesting part of the design, creating the teeth. To make things easier, I could have used FreeCAD's sprocket tool, which generates the teeth automatically, but I find it doesn't give enough control. That's why I'm doing it manually. The goal is to create the cutouts where the chain rollers will fit. To do this, start by creating a sketch on the XY plane. Then, using the External Geometry tool, project the large outer circle. To make it easier to see, I'll hide pad 1 in the tree view. Next, with the Circle tool, draw a circle at the origin. Using the Dimension tool, we'll assign a diameter driven by a variable. Click on FX, enter diameter chainring chain, and then click OK. Next, select both circles and convert them to construction lines. Now we'll place the chain rollers. Using the circle tool, create a circle on the large inner circle and give it a diameter of 7.92 mm. Then select its center and the green axis and use the coincidence constraint to make them coincident. With the circle tool, create a second circle and place it on the large inner circle. Then select both circles and apply the equal constraint. These two circles are just for construction, so select both and convert them to construction lines. Then with the dimension tool, set the distance between their centers to 12.7 mm. This value matches the pitch of a bike chain. Now let's draw the shape of the teeth. Using the line tool, draw two lines starting from each of the circles and ending on the outer circle. Make sure to do this for both circles. Next, we need to make these lines tangent to the circles. To do that, select a line and the circle, then apply a tangent constraint. Repeat the exact same process for the second line. Since all the teeth are the same, select both lines and apply an equal constraint. Then with the dimension tool, set the distance between the two lines to 2.5 mm, which corresponds to the tooth width. After that, the sketch should turn green. Next, select only the left line and convert it to a construction line, since we only need the one on the right. Then using the line tool, draw another line on the opposite side of the green axis, starting from the circle and ending on the large outer circle. Select the top point of the line, then the green axis, and then the top point of the opposite line and apply a symmetry constraint. My sketch turns green, meaning it's fully constrained, because when I drew the line, a tangent constraint was automatically created with the circle. If that didn't happen for you, just apply a tangent constraint manually between the circle and the line. To finish this sketch, we just need to close the contour. For that, we'll use the 3-point arc tool. You might need to expand the menu to see it. Then, using the tool, place the first point on the top end of one line, the second point on the other line, and the third point anywhere you like. Do the same for the bottom points of the sketch to draw a half circle. Next, select the origin of the bottom arc and the inner circle and apply a coincidence constraint. For the top arc, select its center and the horizontal red axis and apply a coincidence constraint. If you see an error message, don't worry. I'm using the 1.1 dev version, so the issue might come from that. The sketch is fully constrained, so we can exit it by clicking the close button. Now make pad 1 visible again, then with sketch 2 selected, click on the pocket tool. We're going to remove material all the way through. In the task menu, set the mode to symmetric and the type to through all, then click OK to confirm. Since we're not cavemen, we're not going to recreate every cutout one by one. Instead, we'll use a polar array. With the pocket selected, click on the Polar Pattern tool. In the task menu under Occurrences, click on the FX icon and enter the number of teeth variable. Then accept and confirm the operation. And tada, you've just created your own custom sprocket from scratch. To test it, you can change the number of teeth value to 50 or 40, and you should see the model update automatically. That's the magic of parametric design. Now let's create a central opening in the chainring so it can be mounted on a crankset. To do this, create a sketch on the XY plane. Using the circle tool, draw a circle at the origin and set its value to 88 mm, which is the standard size for this type of chainring. Then exit the sketch and create a pocket operation. In the task menu, set the mode to symmetric and the type to through all. That gives us a nice big central hole. Now let's create the mounting holes. These are counterbores, which means they have one diameter for the bolt head and another for the screw bolt, as shown in the diagram. For this step, be careful because the holes need to be placed on the back of the chainring. So rotate the part, select the back face and create a sketch on it. Using the circle tool, draw a circle on the green axis and set its diameter to 12 mm. Then with the dimension tool, set a vertical distance of 52, which matches the 104 BCD standard. Next, exit the sketch and create a hole operation. In the task menu, change the head type to counterbore and set the depth type to through all. For the head diameter, enter 12 mm, for the head depth 2 mm, and for the hole diameter 10 mm. Then confirm the operation. In the tree view, select the hole, then click on the Polar Pattern tool. In the task menu, set the number of occurrences to 4 and confirm the operation. Now let's work on the large central opening to start giving this part some character. First, rotate the part, then create a sketch on the XY plane. Using the external geometry tool, project the central circle. Then with the Circle tool, draw a circle at the origin. Using the Dimension tool, set its diameter to diameter chainring chain minus 30 mm. This ensures the opening adjusts automatically as the number of teeth changes. Next, select both circles and convert them to construction lines. Using the Line tool, draw a line starting from the origin at a 45-degree angle. To adjust the angle, press Tab and enter 45. Make the end of the line coincide with the projected circle. This line is important as it will serve as the symmetry axis for our opening. Still using the Line tool, draw 2 lines on either side of the angled line, making sure their ends coincide with the 2 construction circles. We'll make these 2 lines symmetric with respect to the green line. To do this, select the top point of the first line, then the axis, and then the top point of the second line. Click on the Symmetry constraint. Repeat the exact same process for the bottom points. Using the Dimension tool, set an angle of 55 degrees between the top line and the vertical green axis. Also, set a height of 42.5 mm for the bottom point of the top line from the red axis. Next, convert the symmetry line into a construction line. Then, just like we did for the teeth, use the 3-point arc tool to close the sketch, starting with the top arc and then the bottom. Finally, select the centers of both arcs and make them coincident with the horizontal red axis. If, like me, you misplaced the end of the arc, select both points and apply a coincidence constraint. Repeat the same process for the bottom arc. Select its center and the red axis and apply a coincidence constraint. The sketch is now complete and fully constrained, so we can close it. Next, create a pocket operation by clicking the tool. In the task menu, set the mode to symmetric and the type to through all, then confirm the operation. Next, let's round the corners by selecting the 2 vertical edges while holding Ctrl. Make sure to hold Ctrl or it won't work. Then use the Fillet tool. In the task menu, set the radius to 5 mm and confirm the operation. Now let's create a chamfer that goes through the entire thickness of the part. To do this, simply select the top edge and click on the Chamfer tool. In the task menu, set the size to 4 mm. But as you can see, it doesn't work. FreeCAD refuses. You need to trick it by entering a value like 3.9999 and then the chamfer will be created. You can accept the operation once it's done. Next, let's create a polar pattern of the last 3 operations. In the tree view, select the last 3 operations while holding Ctrl, then click on the polar pattern tool. Set the number of occurrences to 4, then confirm the creation by pressing Enter or clicking OK. We can now test if our part still responds to changes in the number of teeth and check that the model isn't broken. In the tree view, open dimensions and adjust the number of teeth to 50. As you can see, the model takes a little time to recalculate, but we get the correct result. Let's set it back to 44, since that's the size we're really interested in. Now we can create the opening above the mounting holes. I chose to separate this operation from the previous one because, depending on the chainring size, the opening may or may not exist. To create this opening, we'll make a sketch on the XY plane. It's kind of the golden plane in this tutorial. Next, using the Polyline tool, draw the shape of our opening, using the vertical axis as a reference. Make a closed shape, making sure the bottom line is horizontal. Then, with the Circle tool, draw a circle centered at the origin. Using the Dimension tool, set its diameter to diameter chainring chain minus 30 mm. This circle will help us constrain the sketch. Next, select the right point of the shape and the circle and apply a coincidence constraint. Then select the left point, the vertical axis, and the right point and apply a symmetry constraint. You need to repeat the same symmetry for the 2 bottom points as well. You also need to make the top point of the shape coincident with the circle. To do this, select the top point and the circle, then apply a coincidence constraint. With the Dimension tool, set an angle of 140 degrees between the horizontal line and the slanted line. Still using the Dimension tool, set a vertical value of 63 mm for the horizontal line, and finally set a value of 17.5 mm for the left point relative to the vertical axis. Before closing the sketch, make sure to convert the large circle into a construction line, so it won't interfere with future operations. We can then close the sketch and create a pocket operation to remove the material. In the task menu, set the mode to symmetric and the type to through all, then confirm the operation. Next, we're going to round the edges of the opening. To do this, select all the vertical edges you want to round while holding down Ctrl, then click on the Fillet tool. In the task menu, set the radius value to 2 and confirm the operation. Now we need to create a chamfer. To do this, simply select the top edge of the contour and click on the Chamfer tool. In the task menu, once again trick the software by entering a value of 3.999 to get a 4 mm chamfer. And now we can create the operation. Now, just like for the large opening, we need to select the last 3 operations in the tree view, then click on the Polar Pattern tool. In the task menu, change the number of occurrences to 4 and confirm the operation. To finish the modeling, we'll add a small 1 mm chamfer on the edge as a subtle detail. Select the edge and click on the chamfer tool. In the task menu, trick the software by applying a 0.99 mm chamfer, then confirm the operation. The modeling of our bike chainring is now complete. I think it's a good time to save your file if you haven't done so already. Now we can move on to creating the paths to machine this part in CNC. But before that, a quick message from today's video sponsor, PCBWay. They're a trusted name for both DIY and industrial projects. I had the chance to test their 3D printing and CNC services to create a bike chainring, and the quality was truly professional. You simply upload your 3D file, select your options, and you're set. Their standard 3D printing options are excellent. Plus, every new customer receives a $5 coupon for their first order. A big thank you to PCBWay for supporting this video. The first thing we're going to do is rename our part by pressing F2 and naming it chainring. Then we still need to create and import a few objects before starting the toolpaths. We'll begin by drawing the dimensions of the stock we're going to use. To do this, let's go into the sketcher and create a sketch on the XY plane. Using the centered rectangle tool, we'll draw a 200 by 200 square to represent the dimensions of our stock. Once it's created, we can close the sketch and rename it helpers with the F2 key. We'll use this sketch to place the bed of our CNC. Since we need to machine both sides of our part, we have to create some positioning points to make sure we can put the piece back in the exact same place. Even the slightest misalignment during machining could be fatal. So let's go to File and Import. Then select our bed and click Open. We can now see our bed appear in the 3D view. Let's start by renaming it to Bed. We'll then move it to align it with the rectangle we just created. Next, by right-clicking on it, choose Transform and apply a rotation of negative 180 degrees along U and negative 180 degrees along W. The goal is to have the missing corner at the top right. On my CNC, the origin point is 15 mm away from the edge of the bed in both X and Y. We still need to move the bed to place it in this position. To do that, let's go into the Draft Workbench and use the Move tool. To do this, first select the bed in the tree view, then click on the Move tool. With the snapping tools enabled, select the bottom point of the bed, then press Y to constrain the movement along the Y axis, and snap it to the bottom left corner of the rectangle. If you can't snap correctly, make sure these snapping options are checked in the snapping menu. Repeat the same process to align the left side of the bed with the left side of the rectangle. Use the Move tool again, select the left corner of the bed, press X to constrain the movement along the X axis, and snap it to the left corner of the rectangle. Finally, we just need to position the bed correctly according to our machine's origin. To do this, go to the bed's properties in the left menu, in the position settings, and set Z to -2 mm, subtract 15 mm from the X value, and also subtract 15 mm from the Y value. This allows us to precisely determine the positions of the holes we'll use to secure our stock to the bed, ensuring the best accuracy when flipping the part during machining. To do this, we'll project these holes into our helpers sketch. Double-click on helpers in the tree view. Then, using the external geometry projection tool, project the 3 holes that will be used to secure the stock. Since we'll be flipping the plate, we need to create mirror equivalents of these circles. To do this, select the circles and use the Symmetry tool. Then select the vertical axis and click to confirm the operation. The 3 new circles are construction lines, so select them to convert them into solid lines. You can then close the sketch. We can then hide the bed as we won't need it anymore and finally switch to the CAM Workbench to start creating the toolpaths. Before diving headfirst into creating the toolpaths, it's important to be well prepared. This isn't like 3D printing where you just hit slice and the software does everything automatically. You absolutely need to know the capabilities of your CNC and the different bits you'll be using. In my case, I'm using a Carvera Air, which is a desktop CNC that mainly uses 3.175 mm diameter bits. Since we'll be machining aluminum, we need to pay attention to the different tool speeds as well as the milling depth. We also need to tell FreeCAD how to generate the code so that it can be correctly interpreted by our CNC. It can be a bit intimidating at first, but I'll guide you and you'll see that it's easily manageable. The first step is to create a job. To do this, click on this icon. In this window, FreeCAD asks if we want to use a template to create our job. Since it's our first time, we don't have one, so leave it set to none. Next, we need to select the objects we'll use to create our toolpaths. As expected, go to the Solids menu and check Chainring. The bed won't be needed here. Then in the 2D menu, check Helpers, because this object contains the positions of our mounting holes. Once both boxes are checked, click OK to confirm. You should then see the Job Edit window appear. This is a very important window where we'll need to make several settings. The first tab, General, corresponds to the first window we saw. This is where we can add any objects we might have forgotten when creating the job. Next, the Output tab is where we tell the software how to generate the code for the CNC. For the processor line, you need to know which one your machine uses. This is usually indicated by the manufacturer. If it's a small desktop CNC, the processor is generally GRBL, which handles 3 axes well. For semi-professional or professional machines, the Linux CNC processor is often more suitable. In my case, I used the Linux CNC processor for the Carvera, and everything worked fine even though GRBL was recommended by Makera. For the coordinate system, since we'll be machining only one part on this bed, leave G54 checked. In the order by setting, I recommend checking operation. This way, if you're a beginner, it's often easier to organize your operations in the order they will be executed and avoid mistakes. I also suggest checking split output. This means that when exporting your code, you'll get a separate file for each operation, which you'll run one after the other. This allows you to pause between operations to verify that everything went well. Sure, it requires a bit more handling, but it can help prevent errors. The next setting is Setup. In this window, you can enter the dimensions of your stock. By default, FreeCAD suggests creating a stock based on your 3D model with a 1 mm offset on each face. Personally, I prefer to create a box by entering the exact dimensions of my aluminum plate. In my case, the plate is 200 by 200 by 4 mm, so I choose Create Box. Since I selected both the 3D model and the sketch with the rectangle, FreeCAD automatically proposes the correct dimensions. You can always adjust them if needed. Next, a very important setting is the origin placement. For cases like this, I prefer to place it at the same location as my machine's origin. Here I want the origin to be at the bottom left corner of the top face of my stock. I always recommend placing it here. To set it, select the point on the stock and click the Set Origin button. You should see your models and the stock move to the position of the gizmo. Since we want to flip the part halfway through machining, it's highly recommended to center our 3D model in the middle of the stock. Here it's already centered, but sometimes your model might not be. In that case, go to the model folder in the job, select your model and click Center in Stock. This will align the two objects with each other. As for the sketch, we can see it's placed in the middle of the stock. However, I'd like it to be positioned at the bottom. We can move it, but not in this window. We'll do that later. The next setting is the tool selection. In this window, you can choose from the tools you've already created and set their speeds here. Since we're starting from scratch, we'll need to create them, and I'll show you how to do that in another window. The other two tabs won't be needed for our case, so we can leave their settings as they are and click OK to confirm the job creation. So now we're going to set up our tools. This is a fairly simple project and we'll only need two different tools. First, a 3.175 mm end mill, which will be used for the various cuts. This is the tool we'll use the most in this machining. The second tool is a 90-degree chamfer bit, also 3.175 mm in diameter. It will allow us to create the chamfers without a stepped effect and achieve a professional finish. I'll show you how to create them. Before that, let's delete the default tool placed in the Tools folder of the job, as we won't need it. Next, click on the Tool selector in the toolbar. In the window that opens, FreeCAD shows a library of pre-made tools. We're going to create a new one. To do this, click on Open Library Editor. In this window, click on Create a Tool Bit. The software will then offer templates to create your bit. In our case, we'll start by creating an end mill, so click on the end mill preset. You'll then see a new line appear at the bottom of the table labeled End Mill. To modify its properties, double-click on it. We now have access to all the different parameters. To get the specs for your bit, you can either refer to the manufacturer's manual or use a caliper to measure the bit directly. In this case, I'm going to name my tool 1/8 end mill 3.175 mm metal. I'll leave the first two settings as default, then set a cutting edge height of 12 mm, a diameter of 3.17 mm, number of flutes to 1, a length of 38, and a shank diameter of 3.17 mm. We can then click OK, and you'll see that the tool has been created. Now we're going to repeat the same process to create the chamfer bit. Click on Create Tool Bit. From the presets, select Chamfer, then double-click the new line in the table to open its properties. I'm going to rename this tool 1/8 chamfer 93.175 mm. We'll keep the first two settings at their default values, then set the cutting edge angle to 90, the cutting edge height to 1.59 mm, the diameter to 0.1, the number of flutes to 2, the length to 38, the shank diameter to 3.175, and the tip diameter to 0.1. Finally, click OK to finish. You can now click on Close. Back in the main window, you should see the two new lines for our tools. To import them into our job, simply double-click on each one. You should then see them appear on the left inside the tool folder. You can then close the window. We will now modify the default parameters. To do this, double-click on the Setup sheet. In the task menu on the right, scroll all the way down to adjust some parameters such as the step down. By default, it is set to match the diameter of our tool. I find this value way too high for our machine and our bits, so I'll set it to 0.2 mm. This means that with each pass the tool will remove 0.2 mm of material. It may sound small, but for aluminum with this type of bits and machine, it's actually quite a high value. Below that, in the height section, we can set how high the tool will travel when moving. In my case, I'll only have a few screws on the bed, so I can leave these values as they are. But if you're using clamps taller than 3 mm, I recommend increasing this value, otherwise your tool might collide with them, and that would be a disaster. Next, in the tool controller option, we'll set the feed rates for the machine head. For this CNC, I can set 1200 mm per minute for the horizontal feed and 700 for the vertical feed. These values correspond to the movement speeds when the spindle is not actively cutting. Then we can click OK to confirm. The last and most important settings are the feed rates, plunge rates, and spindle speeds of the tools. To adjust them, go to the tool's properties. Simply click on the tool and in the table below you'll have access to the data properties. For the end mill, I'm going to set a horizontal feed rate of 500 and a vertical feed rate of 200. Below that, I'll set the spindle speed to 12,000 RPM and assign tool number 1. For the chamfer bit, we'll set a slower horizontal feed of 350 and a vertical feed of 200. We'll set the spindle speed to 12,000 RPM and assign tool number 2. I reduced the speed because it gives me a better surface finish. We're going to machine both sides, starting with the bottom face. But as we can see, the part is currently facing upwards, so we need to rotate it. To do this, we go to the data properties of the chainring model. In the placement option, under axis, we'll change the rotation axis to x equals 1, y equals 0, and z equals 0. Then in the angle field, we'll enter 180 degrees. In the viewport, the part should flip over while staying in the same position. It's a bit hard to see because the part is semi-transparent, but the rotation went fine. Now we need to move the helper sketch to the bottom of the stock. To do this, go to its data properties, then placement, position, and set the Z value to -4. Now that all our parameters are set and all the parts are in place, we can start creating the tool paths. We'll begin by making the holes to fix the plate. For this, we'll use one of the most commonly used operations, the profile. Since these are small holes and our end mill is 3.175 mm, it will remove the material similarly to a pocket operation. To create this operation, click on the Profile tool in the toolbar. The software will ask us which tool we want to use. Since we want to remove material, we'll select the end mill. In the menu that opens, go to the Base Geometry option. While holding Ctrl, select the 6 circles where we want our holes, then click Add. Next, in the depth parameter, we can see that the machining will start at 0 and go down to -4, which matches the thickness of our plate with a step down of 0.2 as we set earlier, so we can leave the settings as they are. In the height option, these are the heights at which the tool will retract during its movements. We can leave these values as they are. Next, the operation options are very important parameters. Here you can change the selected tool or specify whether to use coolant. You're asked whether you want to make the cut inside or outside the circle. In our case, we want to remove material inside the circles, so it should be set to inside. For the direction, I've been using clockwise so far and the results have been good, so I recommend leaving this parameter as is. Finally, there's the extra offset option. Here we'll leave it at 0, but you'll see that for finishing passes, this is an option worth considering. Next, make sure the Use Compensation box stays checked. This option offsets the path relative to the diameter of the cutter. For example, if you uncheck it, the center of the cutter would follow the circle path, resulting in a hole larger than intended. So it's important to keep this box checked. You can then click OK to confirm the operation. In the viewport, the different paths for creating the openings will appear. At first glance, it looks like the operation is going well. To be sure, we can use FreeCAD's preview tool, the CAM simulator, to check the result. This tool is really what will help you avoid mistakes and understand what might be wrong in the generation of your path. Here I'm increasing the speed to get a quick preview, and as you can see, we do get proper holes going through the plate in the right places. Once you're done inspecting the preview, I strongly recommend closing it completely and not just minimizing it, otherwise it can cause FreeCAD to crash. We can close the path simulator by clicking on Close. Now let's move on to creating the tool paths for the mounting holes. These holes are a bit special because they are counterbored. Since they involve two different cutting diameters, they are more complex than the previous holes. To create them, we'll use the 3D pocket operation. To do this, we'll start by selecting only the inner faces of the top hole. You need to select all 4 faces, then we'll use the 3D pocket operation. In the task menu, go to Base Geometry and you will see that the 4 faces have been correctly selected. Then in the Depths tab, you can see that the machining starts at 0. However, we don't have access to the final depth value because FreeCAD determines it automatically. The step down is correctly set to 0.2, so we can move straight to the Operation tab. We can clearly see that our tool, the end mill, is properly selected. In the Cut Mode tab, we'll leave it on Climb. This gives a better surface finish. If your machine isn't very rigid, you might want to use Conventional instead. It's a bit gentler on the machine. Next, for the pattern parameter, I usually set it to Offset. This lets you follow the shape you're cutting. In this case, we'll use this pattern for 100% of the operations, but you can try others to see if they work better for your project. The step over percent parameter controls how much the tool overlaps between each pass. A value of 100 means there's no overlap at all. I usually set it to 50 or 60 to make sure all the material is removed and the result is smooth. Then we leave the pass extension at 0 because we want the cut to follow the shape precisely. Now we can exit the operation and see what happens. As you can see, even though we selected all 4 faces, the operation only runs on 2 of them. Sometimes the operation might not even be created at all. The second issue is with the hole creation. It doesn't happen in one go. I'll show you in the simulator. You can see it jumps from one hole to another, almost like the machine is cutting in layers, and it waits until one is finished before moving on to the next layer. That's pretty disastrous for machining time. Let me show you how to fix these 2 issues. First, let's close the simulator. Then double-click on the 3D pocket operation in the tree view. The first thing we're going to fix is making the holes cut in one go. To do that, in the Operation tab, check the box for Use Start Point. That's the one that solves the problem. You can also check Min Travel, which can help reduce machining time as well. Then we can accept the operation. In the viewport, we can already see there are fewer red lines. Let's open the CAM simulator to check the result. And now we can see the holes are cut one after the other, which is much better. And now you might be asking, yes, but Jami, how do we get the other 2 holes that are still missing? The answer is really simple. Go to the data properties of the 3D pocket, scroll all the way down, and check the box called Adaptive Pocket Finish. Once you enable that, you should see the tool paths appear for the other 2 holes, which is exactly what we wanted. You can run the simulator again if you want to double check, but everything should be fine now. Now let's take care of creating the surfacing for the teeth. As you've probably noticed, the teeth don't have the same thickness as the chainring, so we'll need to machine a recess. To do this, we could use a pocket operation, but that would follow the exact shape of the teeth, and depending on the size of the end mill, it might not go through everywhere. The best solution I've found is to create a flat donut shape that we'll use for the machining. Let me show you. We'll go into the Part Design Workbench to create the donut. Once we're there, we'll create a new body. Press F2 to rename it Teeth Surfacing. Then select the surface of the teeth in the viewport and click on the Subshape Binder tool. This projects the chainring face into our body. After that, we can hide the chainring by clicking on the little eye icon next to the job. Next, we'll create a sketch on this binder. To do that, select the yellow face and click on the Sketch tool. Using the External Geometry tool, project the inner circle into our sketch. Then, with the Circle tool, draw a new circle with its center placed on the projected circle's center. Finally, use the Dimension tool to set its value to the variable diameter chainring chain plus 18. We can now close the sketch. Let's create an extrusion, so click on the Pad tool in the toolbar. In the Task menu, check the reversed box, set the thickness to 3 mm and then click OK to confirm. To keep our file organized, we'll create a folder to store our models, so they're clearly separated from the CAM objects. To do this, click on the Folder tool in the menu bar. This will create a folder in the tree view. Press F2 to rename it Models. Once it's renamed, we'll drag and drop the chainring, the helpers, the bed and the teeth surfacing into it. And we'll place it above the job. Next, we'll hide our Models folder since it might get in the way. Now I'll show you how to import a new solid into our job. To do that, go back to the CAM Workbench and double-click on the job in the tree view. In the Job Edit, go to the General tab and click on Edit. In the window that opens, check the box for teeth surfacing and click OK. In the viewport, you'll see the flat donut appear in blue. In theory, it should be placed in the correct position. Then we can accept by clicking OK. Looking at the viewport, I noticed that the flat donut is very close to my positioning holes and quite far from the teeth. Once again, we can fix this thanks to the magic of parametric modeling. To do that, I'll open my Models folder, go into Teeth Surfacing, then into Pad 2, and double-click on the sketch. Next, I double-click on the dimension, then on the FX icon, and instead of 18 mm, I'll put 14 mm. I click OK, and then close the sketch. And there we go. Miraculously, the donut updates automatically in my job. Before moving on, I'll just check in the viewport to make sure the donut is properly placed. Everything looks good. Now we can move on to the surfacing. To do this, we'll use the Pocket Shape tool from the toolbar. The goal is to select the flat surface of the donut, but there are quite a few objects that can get in the way. You need to go to the tree view and hide the model chainring and model helpers. Then you can comfortably select the face. In the Task menu, go to the Base Geometry tab and click on Add. The face should now appear in the box. Next, go to the Depth tab. You'll notice that the values aren't correct at first. Actually, you just need to click once to update them. Now we can see that the operation should start at 0 and go down to -1 mm with a step down of 0.2. So everything is fine here. You just needed to click on the value to update it. Next, go directly to the Operation tab. Here we can see that the end mill is properly selected. Just like we did for the 3D pocket, we'll change the pattern to Offset and set the step over to 60 for good coverage. We can check the min travel box to slightly reduce machining time. Then we can click OK to generate the toolpaths. We finished generating the toolpaths for this face. We can run the CAM simulator to see how all our operations turn out and check that there are no errors. I want to add a small chamfer on the side of the teeth to make chain engagement smoother. I didn't model it directly because it could have caused issues with the other toolpaths. Instead of adding it later on each tooth, I'll create it now as a circle. To do that, I'll go back to the helper sketch and double-click on it. With the Circle tool, I'll create a circle at the origin. Then with the Dimension tool, I'll set its value to diameter chainring chain plus 6.6 mm. This value matches the outer diameter of our sprocket that we referenced earlier. Next, I can close the sketch. To create this chamfer, we'll use a profile operation. To make it easier to see and select the sketch, I'll first hide the other toolpaths we've already created. Then I'll click on the Profile tool. In the Task menu, I'll go to the Base Geometry tab. Then in the Tree view, I'll hide the Model Chainring and Model Teeth Surfacing, so only the helpers are visible. In the Viewport, I'll select the circle, and in the Task menu, click Add to include it. Next, in the Depth tab, we'll set the starting height for the machining. The tooth surface is 1 mm below the base surface of the chainring, so we need to enter -1 mm. Here we'll use a 90-degree chamfer bit. In our case, we want a 0.5 mm chamfer. To create it, the bit needs to follow this path at a depth of 0.5 mm. That means in final depth, we enter -1.5 mm. Since the chamfer is very small and our bit can create a maximum chamfer of 1.6 mm, we can just do a single profile operation and step down gradually until we reach the chamfer depth of 0.5 mm. If we wanted a 4 mm chamfer, for example, we'd need a larger bit or another technique, which I'll show you later. Next, in the step down, I'll change the value to 0.1 mm. This gives a better surface finish and a clean result with the chamfer bit I'm using. Next, in the Operation tab, make sure to select our chamfer bit instead of the end mill. This bit will give us the chamfer shape, so it's important to change it. The cut side setting doesn't matter, because we want the bit to follow the circle exactly. Instead, make sure to uncheck Use Compensation. Once that's done, click OK to accept the operation. In the viewport, you should see the 5 toolpaths for the chamfer. To check the operation, we'll run the CAM simulator, showing only the last 2 operations. As we can see at the end of the simulation, the chamfer has been created on the teeth. Perfect, we can now exit the simulator. Now we'll rename the job and the operations to keep our file organized. We're going to create a second job for the other side of the sprocket. First, rename the job to bottom face. Then rename the first profile operation to holes placement, the 3D pocket to holes fixations, the pocket shape to surfacing teeth, and the second profile to chamfer teeth. This step is really crucial to avoid getting mixed up with the operations and the machining order. For machining the top face, we'll create a second job. Since we're not cavemen, we won't start from scratch. We'll duplicate the job we already have. This lets us keep all the settings we've already configured, like the processor for generating the code, the stock, and the tools we created. To reuse these settings, we'll first export our job as a template. To do this, go to the CAM menu and select Export Template. In the window that pops up, you can see the different settings that will be exported, like the tools, the setup sheet, and the stock. The default options are fine, so we can leave them as they are and click OK. I recommend saving your template in FreeCAD's default folder, otherwise it will be hard to import later. So stay in the macros folder, then give it an easy to remember name. In my case, I'll call it bike chainring and then click Save. Now I can hide the bottom face job, then click on the new job icon in the toolbar to create a new one. In the window that opens, I can choose my bike chainring template and then select only the chainring model, since that's all we need in this job. Then we click OK to create it. Depending on your computer and the complexity of the template, this may take a little time to create. In the Setup tab, we can see that the stock dimensions were kept, but the sprocket isn't centered. To fix this, click on Center in Stock. The part is now properly centered, and we can also see that the origin is correctly placed. In the Tool tab, both of our bits are present. In the Output tab, the settings we made are also there. So everything has been preserved. We can click OK to confirm. To keep the file organized, press F2 and rename Job 1 to Top Face. Since our part is symmetric, the teeth are centered on the chain ring, so we'll need to repeat two operations from the previous job, the teeth surfacing and the teeth chamfer. To do that, go back to the bottom face job. In the operations, right-click on surfacing teeth. In the drop-down menu, click on Copy Operation. We can see the operation was copied. It's placed inside the bottom face operations. To move it to the top face job, just drag and drop the copy into the operations folder of the top face job. We also need to copy chamfer teeth and drag and drop it into the top face as well. Now we can take care of the openings on this face. I'll show you two methods for making the small openings. The first one is a vanilla version, meaning only with FreeCAD's built-in tools. We can make the opening using a 3D pocket, just like we did for the fixing holes. To do this, click on the 3D pocket tool in the toolbar. This operation is on the top face, so we select the job top face. In the viewport, hold Ctrl and select the inner faces of the opening. Then in the Base Geometry tab, click Add. Next, go to the Depth tab. Just click on the Start Depth value so it updates. Then go to the Operation tab. Make sure to change the tool controller to the end mill. Set the pattern to Offset. Adjust the step over to 60. Optionally, check Min Travel to save some time. Then click OK to create the operation. On paper, the operation works fine, it gives the result we want. But the tool removes 100% of the material. That makes machining very long, especially for big holes like the sprocket center. Unfortunately, FreeCAD has no 3D contour tool, so we're stuck with this method. And we also need a finishing pass to smooth the surface. That means running the same path again, often just cutting air. We can also see that making this opening takes around 14 minutes, which is quite long. The second method, which I find more elegant, is to use a macro. This one was made by Tarman, a big contributor to the CAM Workbench. It's called Wire 2 Profiles. You can download it directly from his GitHub page, link in the description. He also made other macros you might find useful, so feel free to check them out. Let me show you how to use it. The first step is to create a profile operation, making sure to do it on the top face. Next, we need to select the edges of the opening. To do this, select one edge, then click the Loop Selection tool and click Add. Next, in the Depth tab, click on the Start Depth value to update it. You can leave it as it is. Then go to the Operation tab. Make sure the tool controller is set to the end mill. Set the cut side parameter to inside. Since this is a roughing pass, we need to leave material for the finishing pass. So we add an extra offset of 0.2 mm. Then click OK to create the operation. For now, nothing fancy, just a toolpath created on the top face. To make the macro work, select the profile and then a vertical edge of the surface you want to machine, like this one for example. Then run Tarman's macro. And magic! The toolpath is duplicated along the second edge you selected. As you can see, this creates far fewer paths than the first method I showed. Let's run the CAM simulator to see how it looks. We'll select only the last operation to get a preview. As we can see in the simulation, unlike removing the whole opening, here we only follow the inner contour, which greatly reduces machining time. However, you can see it creates a stair-step effect, and the surface isn't smooth at all. I'll show you how to fix this. We can close the simulator. The macro we just ran isn't linked to the profile, which means if we modify the profile, the toolpath won't update. To do the finishing pass, we can reuse the basic profile operation, so double-click on it to open it. In the options, we'll change the tool controller to the chamfer bit. We'll also remove the extra offset by setting it to 0. Then we can exit the operation. We'll reuse the macro to create the finishing pass. To do this, hide the previous operation, then select Profile 3 and an edge of the surface. Finally, run Tarman's macro. We can make the roughing pass visible again and run the simulator to see how these two operations work together. Now we can see that we've got a nice smooth surface, which is perfect. However, we can notice that the chamfer bit, because of its small size, might struggle to cut all the way through, so we'll need to create an additional profile operation. We'll hide the last two operations, then create a profile operation by clicking on the profile icon in the toolbar. Next, make sure to set the operation in the top face job, then in the base geometry tab, select one edge at the bottom of the opening and click on the loop tool. However, we can see that the selection doesn't work. That's fine, we'll just select each edge one by one and click Add to bring them into the operation. Then in the Depth tab, set the start depth to -3.80, so we only make a 0.2 mm pass at the edge of the opening. Next, in the Operation tab, set the cut side to inside and make sure to select the end mill as the tool controller. Then we can confirm the creation of the operation by clicking OK. We can see in the viewport that the operation has been created in the right place. You can also check with the simulator to make sure everything is working correctly. We're starting to have quite a few operations, so let's rename them to keep things organized. Profile 3 becomes Profile Macro Small Opening. The first end mill is Small Opening Rough. The second end mill is Small Opening Finish, and Profile 4 becomes Small Opening End. We can see that we now have all the operations for a single opening. Next, let's see how to handle the others. The sprocket is symmetrical along the X and Y axis, so we can use a polar array to duplicate the toolpaths. This avoids recreating them one by one, which would take a lot of time. I'll show you how to do this for the small opening rough. Select the operation in the tree view, then use the array tool in the toolbar. Next, in the data properties on the left, scroll to the bottom and change the array type to polar. Set the angle to 270. You also need to change the rotation center. By default, it's at the origin. Since our stock is 200 by 200, shift it by 100 in X and 100 in Y. Finally, set the number of copies to 3. Let's rename the dress up operation to Array Small Opening Rough. Now all that's left is to do the same for the finish pass and the end pass. I'll speed up the video here because it's exactly the same as what we just did. It's been 47 minutes since you started following this tutorial, and I really want to thank you from the bottom of my heart. I'd love to know what we should model next after this sprocket. If you want more content on CNC machining, woodworking, mechanics or BIM, don't hesitate to let me know in the comments. Either way, thank you so much for still being here. Now we'll move on to the large central opening and use the same technique as for the small opening. Let's start by creating a profile operation on the top edges. Make sure to select the top face job, then pick a top edge of the large opening and use the loop tool to select the entire contour. Once you've checked that everything is selected, go to Base Geometry and click Add. Next, in the Depth tab, update the value by clicking on Start Depth. You should see 0.2 appear as the value. Then in the Operation tab, make sure the end mill is selected. Set the cut side to inside. Since this is a roughing pass, add an extra offset of 0.2 just like we did earlier. Then confirm the creation by clicking OK. Next, we'll use Tarman's macro. Select Profile 5 in the tree view, then pick an edge of the surface, like this one for example, and run the macro. After a short calculation, you should see the different toolpaths appear as expected. Next, we'll repeat the same process to create the finishing pass. To do that, double-click on Profile 5 in the tree view, then in the task menu switch the tool controller to the chamfer bit and remove the extra offset. Then hide the last operation, select Profile 5 and an edge of the surface and run the macro. You should now see both operations, the rough and the finish. However, we can notice that the toolpaths don't perfectly follow the contour, especially around the holes. That's normal. We'll create one more operation to complete this path. But before that, let's rename Profile 5 to Profile Macro Big Opening, the first end mill to Big Opening Rough, and the second end mill to Big Opening Finish. Next, we can hide the last two operations to keep the viewport clearer. Then we'll create a profile operation. Click on the icon in the toolbar and make sure to select the top face job. In the viewport, select the bottom edge near the mounting hole, then go to Base Geometry and click Add. Next, in the Depth tab, make sure the start depth is 0 and the final depth is -4, then move on to the Operation tab. For the tool controller, make sure to select the end mill. You can leave the other options as default and click OK. And patatra, the toolpath doesn't get created. Actually, this is a bug in FreeCAD. When you ask it to make a profile on an open contour, it struggles to determine the end of the machining. To fix this, go into the Profile and in the Depth tab, set the final depth to -3.8 instead of -4. Then you can exit the operation. Now your toolpath should be created correctly. As you can see, this path needs to be duplicated 3 more times. We'll use an array operation just like before. I'll speed up the video since it's exactly the same process. Once duplicated, let's rename the operation to Array Cut Inside. Just like with the small openings, the chamfer bit might not cut all the way through the stock, so we'll add a profile operation to follow the lower interior contour of the large opening. To do this, click on the profile icon in the toolbar. Make sure to select the top face job. Then select the bottom edge and use the loop tool. It's possible, as here, that the tool won't select the entire loop, so you'll need to manually pick the missing parts. Then go to Base Geometry and click Add. Go to the Depth tab, set the start depth to -3.8 and leave the other values as they are. Click the value to update it, then in the Operation tab, make sure the tool controller is set to the end mill and change the cut side to inside. Finally, confirm the operation. Before running the simulator to check that everything is working correctly, let's rename Profile 7 to Big Opening End. Next, run the simulator using the rough path, the array and the big opening end. We can see that the cut follows the slopes nicely. Then when we move to the array, it removes the material correctly to match the 3D model. Finally, we can also see that the piece is properly cut at the bottom with the big opening end operation, so everything is working as expected. We only have 2 operations left. Let's start by creating the chamfer on the outer edge of the sprocket. For this, we'll use the same technique as we did for the chamfer on the teeth. Once again, we'll use a profile operation. Click on the icon in the toolbar and in the next window, make sure to select the top face job. Next, in the tree view, select the lower edge of the chamfer, then go to the Base Geometry tab and click Add. Next, in the Depth tab, click on the final depth value to update it. Since we want a 1 mm chamfer, the final depth should be set to -1. For a better surface finish, we can also reduce the step down by setting it to 0.1 instead of 0.2. In the Operation tab, make sure to uncheck Use Compensation and set the tool controller to the chamfer bit. Then click OK to confirm the operation. If you are unsure, you can run a simulation with the teeth surfacing and the last chamfer. As you can see, everything is happening as it should. Next, let's rename Profile 8 to Chamfer Outside. Finally, after all this time, we're going to create the last operation, which is the final cut of the teeth. And to do this, I'll let you guess which operation we're going to use. It's one we haven't used at all until now. And yes, it's the profile operation. As usual, make sure to select the top face job. Here's a trick for selecting the edges of the outer contour. Don't select any edge at all. It might seem counterintuitive, but it works. In the Operation tab, make sure the end mill is selected and leave the other parameters as default. Then go to the Depth tab and set the start depth to 1 mm. Next, change the final depth to 3.2 mm to ensure a full cut and that the teeth separate properly from the stock. Finally, click OK to confirm. And there we have it. The teeth are fully cut without having to select the outer contour. You can run a simulation to see if the teeth are machined correctly along with the surfacing and the chamfer at the tips. As we can see in the simulation, the result is exactly what you would expect. So now we have all our toolpaths to machine the sprocket correctly. You could also reorganize the operations to reduce the number of tool changes. After that, it's up to you how you want to organize things. The final step is to export the toolpaths. Since we checked the split output option, each operation will be exported to its own file. To export the toolpaths, simply select the job you want to export and click the post-process icon. Then just click OK in each window that opens and choose an export path for your files. You now have all the tools you need to machine this bike sprocket at home. Don't forget that you can download the 3D files for this model for free on my Ko-fi page. The download is free, but you're welcome to leave a donation if you want. I've shared with you my secrets for using the CAM Workbench, and I hope you'll make good use of them. Don't hesitate to like the video if it helped you and subscribe to my channel. It really helps me a lot. Thanks for watching the video all the way through.